coming. And so today I'll be talking through how we've been combining computer vision and natural language processing for multitask fashion attribute modeling at Shoprunner. So first off, what is Shoprunner? And Shoprunner is an American-based e-commerce company, and we essentially partner with around 140 retailers, which represent thousands of individual brands. Historically, the core business offering for Shoprunner has been this kind of 2-day free shipping and returns. Yes, very much like Amazon Prime. And more recently, we have been starting to develop out more data products and offerings to help expand our partner retailer capabilities. So at Shoprunner, we have kind of a very specific definition of attributes, as I'm sure most organizations do. So for us, an attribute is a characteristic of a product which can be applied across multiple taxonomy categories. So taxonomy categories are things like that you would find in different sections of a department store. So things like women's shoes and men's shoes. On the other hand, we have taxonomy or attribute categories, which are things like color and pattern. So these are things that can be applied across those various categories. And on the right-hand side here, I have kind of a sample attribute feed that I generated with my models. Essentially, these were parts of presentations to internal product managers at Shoprunner, with the idea that sometimes saying, oh, this model has a macro precision of 0.94 or an F-beta score of 0.9 with a beta of 0.3 is not really the best way to convey things to non-technical types of folks. So what they care about at the end of the day is really how clean of feeds or like how, I guess, clean the product catalog will look when you filter or search by different things. So this is an example of like black and solid. So at Shoprunner, it's important that we be able to standardize essentially the attributes across our entire product catalog, because retailers can report things in whatever way, shape, or form that they choose. So we might have one retailer which reports very generic colors, so black, white, blue, red, etc. But another one that might take a very different, more artsy approach and say, oh, this is obsidian, ivory, cream, midnight blue, dusk rose, etc. And so we need to be able to sort of standardize our millions of products in our product catalog. The second use case we have for these attribute models is actually as feature extractors for other products or sort of things we'll be building out either now or in the future, such as visual similarity or search. So this presentation is roughly going to follow the data science team at Shoprunner's sort of development trajectory for attribute modeling over 2019. So Q1 was really kind of our R&D phase, where we're looking at what types of data should we use, how should we structure our models, and then I'll walk you through the process of kind of the architectures we built out for the component image and text models, as well as our overall ensemble. Q2, on the other hand, is kind of building on the successes we had in Q1 and saying, how can we physically expand the architectures that we have? So as a bit of framing for this part of the problem, at Shoprunner, attribute modeling is kind of a never-ending problem, where we'll never be able to sort of have all the attributes we want, build one unified data set, and then kind of do one round of modeling to kind of solve it and productionalize it. We kind of have to build things in increments and be able to keep continuously adding on sections to our architecture. And that's kind of going to be, I'll talk through two processes. One is sort of a process to physically add on new attribute task heads that I'm currently calling my Franken network process. The team hasn't actually vetted that name, so we'll see if it sticks. And then the second thing is a process that we built out to basically do multitask, multi-data set training to kind of allow us to very easily add on or train those new task heads. Q3, on the other hand, is just going to be kind of wrapping up the presentation and saying what we have going on to the horizon. So Q1. So why images and text? So from our point of view, our products can be represented in a variety of ways. The two main ways of which are these images and text fields. So images, you would say that every product has multiple images per listing, and they encode certain attributes well. So things like color and pattern. Really, if your product images on your e-commerce site are not conveying these attributes, they're really not doing anything at all. And on the other hand, text encodes things like sleeve length, sizing, and cuts particularly well. So you could think of a situation where maybe you're looking at an attribute like neckline, but an image that may physically be occluded. So say the picture is the model from the back. But trying to determine neckline will be basically impossible with that, but the text will usually encode that very well. And since these data sources provide sort of different perspectives on our individual products, the data science team at Shoprunner felt that these would be good candidates for building a larger neural network ensemble. So the other reason that we have this kind of interest in using both images and text is because sometimes our data is just bad in one type or the other. So for this one, the image is great. We can see it's a pair of jeans. We can see various attributes about it. But if you look at the text, we have a very weird series of symbols that have been inserted into the product description. And that on its own may be enough to throw off a solely text-based model. But combination of the two, we might be able to make it work. On the other hand, we have this pair of genes where the image is basically useless, but the text is fairly descriptive. So from the image, I would think this is, okay, maybe this is a handkerchief or tablecloth or something. But based on the product description, it's actually a very expensive pair of Fendi jeans that I wouldn't know otherwise. So now that I've kind of talked through the sort of different data sources of interest and why we think it's good to kind of build these two and combine them, I want to talk through kind of our technical tool of choice, which is multitask learning. And one of the most fun and interesting ways I've seen it described is actually using a pop culture reference with Karate Kid. So in the movie Karate Kid, if you're trying to think of exploring this the problem domain of karate, the main antagonists are these sort of very bullyish looking folks on the left called the Cobra Kai. Essentially, in the movie Karate Kid, they learn karate as a way to beat people up. So they're exploring the domain of karate with this very narrow hypothesis. But on the other hand, we have the Karate Kid, who learns to do karate from a man named Mr. Miyagi. When Mr. Miyagi teaches him karate, he doesn't actually teach him how to fight, how to punch, how to kick. What he teaches him is a series of seemingly unrelated tasks. So things like waxing a car, painting a fence, sanding a walkway. And while these things don't appear to be directly related to the overall problem domain of karate, what these sort of shared context and lessons by learning these tasks help the Karate Kid build up a richer, better understanding of karate as a whole, rather than how the Cobra Kai learned as a way to fight. The Karate Kid learns it sort of as a more generalized version of karate that includes sort of respect, compassion, discipline, and is really a way of life. So at Shoprunner, what we care about is being able to build these models which generalize well and have a good generalized understanding of our fashion problem domain. So in explicit machine learning terms, multitask learning acts as a form of regularization in the network. So you can see it as a network that is trained in a multitask manner and tries to specialize into a specific task. It actually gets explicitly punished by the loss function in training so that it basically must learn a more generalized representation of the problem domain in order to do well. So for us, we have specific attributes like pattern, style, and color, and these all fall in our fashion domain. And basically, we think that by sharing context across these tasks and kind of letting each of them learn together with one another, we can create these good, generalizable, robust models that we can put into production with confidence. So now that I've talked through kind of the background for multitask learning, I can walk through sort of example architecture. And what we do at Shoprunner is a form of multitask learning where it's called hard parameter sharing. So in this type of multitask learning, basically each task shares maybe 99.9% of the features or weights in the network. So this core model could be anything, really like a CNN, LSTM, any network that you want to train to a particular domain. Then you pipe these features into a series of linear task heads. Then in training, what happens is you feed a sampler batch through the core model, the task heads output their probabilities or scores, and you can generate these losses per individual task. Then what you have to do is combine them into some sort of unified batch loss that you can use for backpropagation. And while this sounds complicated or potentially hard, really what you end up doing is you end up adding these things together. So it's actually pretty simple. So this is what we found to be effective at Shoprunner and also in like kind of various research papers we read up to our R&D period. And in the event that one of these losses starts to get much higher than another just for a specific task, you can actually scale those losses accordingly so they're more in line with one another. Yeah. So now that I've talked through kind of that general architecture, I want to talk through kind of our general training protocol, which would be pretty similar if you've done sort of like various deep learning things. So the first thing we do is we randomly initialize new layers. So typically for us, these are the task heads that we're trying to add on to our existing networks. You then freeze the pre-trained sections of the networks and then aggressively train the randomly initialized sections with high learning rates. And at this point, you'll usually get those new layers up to a point where they have like some domain knowledge, but won't be state-of-the-art. So really to push it up to that state-of-the-art level, what you end up doing is unfreezing the entire network and training the entire thing at a low learning rate. And there's a couple different ways to do that. So like a very vanilla way would be just to assign a low learning rate and train the entire network. But other groups, so say like FastAI, the kind of way that they recommend doing this is assigning sort of a gradient of learning rates throughout their network. Or something I found to be effective with these is just to assign different sections of the network different learning rates, depending on like how pre-trained that section is. So now I've talked through the general stuff, we're just going to dive into the architectures. So our image model architecture starts out with two inputs. So right now we're using a full product image and then a center crop of that original product image. So I'll get into that sort of next couple slides. But both of these are fed one by one through a core ResNet 50 model. And this is essentially a ResNet 50 model that we've kind of fine-tuned to our specific fashion domain. And what we do here is we take the penultimate layer of that ResNet 50, which is a vector of 2048, and we essentially concatenate these together to make a combined vector of 4096. And that combined vector is something that we feed through a dense network. So here, that dense network is really trying to kind of condense these features down to something more digestible for our linear task layers. And that kind of is the general structure for our custom CNN architecture. So the interesting part of that was really that we decided to use this full image and the center crop of that original image as inputs into this network. And it was kind of driven by discussions or brainstorming our data science team had very early on in this process, where we're thinking that we actually get product images from our retailers at fairly large, fairly high resolution, like 2,000 by 2,000 pixels, for instance. And resizing it down to 224 by 224 actually represents a very significant amount of detailed context loss for that image, for that network. So our thought was, if we can find a way to kind of re-inject some detailed context information into the network, we'll be able to perform well on specific attributes which require that kind of detailed information. So the reason that we ended up doing this was actually not because of anything I do data science related, but it's actually kind of a previous career I had as a photographer. So in photography, very early on, you're kind of indoctrinated with certain ways to compose photos. So a very basic thing you do is called the rule of thirds, and it's essentially the idea that you place points of interest in an image on either the vertical or horizontal lines or on the intersections of those lines. But what happens when you pair that kind of, I guess, indoctrination for composition and the fashion domain is that when you look at these tic-tac-toe boards, that center square, really that center crop, gives you a good center of mass shot or detail of that given product. And that happens for most of our cases. And what happens when we add that sort of context injection into the network is we get a couple percentage point boost over just using our vanilla base image model. But the downside here is very much that if our retailers shoot in a way that doesn't conform to that standard, we get center crops which actually aren't that useful. So like this one, we get mostly background, part of the skirt, part of the hand. So not the best center crop and not the best context into the network. So something that our team has been building out in parallel has been doing things like clothing detection, so building in-house clothing models basically tailored to our fashion domain, with the idea we can take these bounding boxes and actually use that as a pre-processing step before the attribute model, so that if we take a center crop of that, we're basically guaranteed to get a good center of mass shot of that product. Then in parallel, something else we are doing is doing sort of clothing segmentation. So the idea that rather than, if we can do something better than just returning that area of the picture and just return like the pixels related to a given product in an image, we can actually run that over our entire product catalog and say standardize it for usage in other deep learning models. So it would be just the product on a purely white background. So it'd be a very clean standard image to pass into other deep learning models. So now that I've talked to you kind of our image architecture and some stuff that we're doing there, I'll get into the, I guess, NLP section. And really, it's leveraging Google's Bert, and I'll talk through sort of the details of Bert in a couple slides. But first, we're going to go through the architecture. So architecture starts out, the fields that we're using are things like product name, description, brand, other info, specialty sizing, et cetera. And we take that, feed that into a core Bert model that has been fine-tuned to our fashion domain. And then really, we just take those features and pipe them into a series of linear task heads. So this is a fairly simple architecture, but this is kind of what folks are using in the NLP field to get state-of-the-art results on NLP tasks. So there's a group at Microsoft which published a paper and nicknamed their model Big Bird, kind of adding on to the questionable Sesame Street naming of these NLP models. But essentially what they did is they found that they could get state-of-the-art results on NLP tasks simply by training Bert in a multitask fashion. Because in comparison to like base Bert, which held the previous benchmarks, the multitask version is forced to find that more generalized representation of those different problems and then generalizes better to the actual task. So we're basically just copying what they have been doing. So Bert is a model that was released at the end of 2018 by Google, and it is a bidirectional model that has been trained to predict out masked words and sentences. So this is a little bit different from a lot of the other language models that have been released in the past year. And so what I mean there is like most language models are trained as here's some section of context and then you generate the right next word in the sentence as kind of how they're trained. But what Bert does is it's actually given the full sentence as context. Certain words in that sentence are then masked out with some probability, and then Bert uses both the left and right side of the sentence around that masked word to predict the masked out word. And Google kind of found that to be a very effective training regimen for their algorithm. And like other language models, Bert's trained on a large corpus of data. So in this case, all of Wikipedia and whatever other corpuses Google felt like including. And really it and the other language models that have been released in the past year are facilitating this very interesting ImageNet moment for NLP, where it's actually quite exciting to be part of the field. Because previously it's been hard to sort of apply state-of-the-art NLP models to specific problem domains because most people have less data than Google, which is not surprising at all. So what happens when Google and other organizations open source these large language models, it means you can take these models which have a very rich understanding of language and apply them to specific problem domains and get state-of-the-art results very quickly. So it's sort of this democratization of NLP. So it's a fun time to be in the field. So in particular, we are using an open source version of Bert, which is maintained by a group called Hugging Face. So yet another kind of interesting name. But what they have done is they've brought this Google TensorFlow implementation of Bert into the Pytorch sort of environment. And they've allowed for loading and saving models, much like other Pytorch models. They've included tokenizer classes, which allow you to pre-process inputs and get them into the correct format for the Bert based on its vocab. And you can really integrate it very straightforwardly into a very standard Pytorch pipeline. So it makes it easy to add on to sort of existing deep learning work that you or your company are doing. So if you're looking for a way to kind of crack some NLP problems, I definitely suggest taking a look at this. So now that I've talked through sort of our component models, I'll dive into a little bit about our ensemble. So the ensemble, really, we start out with the various inputs for the two models that I have talked through already. So it's the full image, cropped image, and the various text fields. We then take our pre-trained models. So these are the models that have been trained to our fashion domain. So the image model, text model, and really use them as feature extractors in this ensemble. So we take the features out of those two models, concatenate them together, and then feed them through another dense network, where this dense network is once again trying to sort of condense these features before they're passed directly into the linear task heads. And what we found by building this ensemble and kind of training both the models end to end and letting them adjust their weights very gradually is we get like another couple percentage point improvement over either of the core models individually. So like while they both perform well, they both have their strengths and weaknesses for certain attribute types. So combining them together kind of lets us make the best of those strengths and weaknesses, and we're able to get a fairly usable and practical, I guess, deep end-to-end deep learning ensemble. So this is kind of like the end of the quarter one stuff, and we've basically shown that we can build these networks, combine them, and get good results. So in quarter two, we're really looking at how do we physically expand these architectures to kind of meet this never-ending attribute problem at Shoprunner. So in expanding the number of categories, there's really two problems that we had. So the first problem we ran into is we have these previous architectures, and how do we physically expand them to include new task heads without throwing away the pre-trained weights? Because if you do this and basically try and take one architecture and force feed it into another, Pytorch will throw you errors, or in the worst case scenario, actually appear to work, but if you aren't careful about it, you'll actually get predictions that are different or evaluation metrics that have changed from your previous iteration of the model. So if you're not very cognizant about that, you'll actually get models that you think are working but are actually terrible, and it's quite scary. So once you can figure out how to add on those new task heads, the next step is basically how to train them. And while we have like very traditional methods, which are based around having a single data set marked with all of our classes, our team at Shoprunner was basically wondering, is there a better way that we can do that? And then if that's like our main objective, our kind of like side mission, side quest is to keep our model count down, with the idea that, one, maintaining lots of models is hard and places a lot of extra burden on our team, since our team is responsible for deploying, monitoring, and kind of maintaining these models. But also because if we start building sort of new models to fit new attribute categories, while that's easy from kind of a modeling point of view, it means that we lose out on a lot of the multitask goodness that I talked to you about previously. So now I'm going to talk to you about sort of this like Franken model process that we use to add on new task heads. So the first step is really just to load up that pre-trained architecture. So this is like the previous round of modeling where you've basically productionized, vetted the model, seen task 1, 2, and 3 all perform fairly well. But now you have to go ahead and add a new task. So what you end up doing is you initialize this random kind of shell of an architecture. So it has all the core components, so core model, task 1, task 2, task 3, and you're really just adding on that task 4. And what you end up doing is you end up slicing apart this old pre-trained model. So you load it up, slice it into its like little pieces of a component structure, and then once you do that, you start slotting it into that husk of an architecture. So core model goes there, task 1, 2, and 3 get put in their respective places. And since these are kind of putting weights into a new architecture and the forward pass in this architecture has already been defined, if you pass data through this new populated shell of an architecture, you actually get the task 1, task 2, task 3 performing at the levels that they were before. And now that task 4 is just the only randomly initialized section you have to worry about. So now when you're at this point, you can actually go ahead and train that new task 4 in whatever way you see fit. So like if you followed our previous regimen, you end up freezing all the other tasks in the core model, training it aggressively at a high learning rate. Once it's at a good point, you can unfreeze everything, train it at a low learning rate, and the end result is you get this model that can now do all 4 tasks at once rather than just 3. And the process that I laid out there is actually so it works very well from like a data science point of view, but from a business point of view, it's actually slightly suboptimal. So from a business point of view, because we're adjusting the weights in the rest of the network, we're kind of creating a completely new model from the one that we had before, even if those metrics are very similar to what they were originally. So right now, that's kind of the process that our team goes through, and we end up having to re-vet most of the model. So in an ideal world, we'd be able to train it and basically only train the weights for that new section, but that's kind of an ongoing piece of work that the team has. So now that we can physically add on those task heads, I just want to go through kind of what the training regimen that we built out for it is. And really, the classic way to approach this problem is you have this one data set to rule them all. You have one data set that's marked with all your categories, and you build one model, you train it, it's good, you productionize it, and you're basically good to go. But for us, because we keep incrementally having to add on these certain categories, if we maintain a large data set, and then basically add on a new category, we don't have that guarantee that that new category will be well represented in our original data set. So we run the risk of a situation where we add on a new category and certain classes are basically non-existent. So then we have to go through, get a new data set, label that completely with both the old and new labels, unify them, and basically keep maintaining things in that way. So this is kind of a very arduous, very kind of expensive process. So something that the team thought would be interesting would be, can we train these multitask models with data sets tailored for each task, rather than just one data set that has all of the tasks contained within it? And really the idea here is that if we can do that multi-data set training, we can build data sets with whatever way makes the most sense for that particular category. So for instance, maybe we have a previous round of work that was done where folks went ahead and labeled a section of our product catalog with a certain set of categories that we might be able to use as an attribute. So that becomes a very low effort way to build that category, whereas other ones we might have to build out manually labeled data sets with like figure 8 or figure 8 or mechanical Turk. So those things we can do, but we don't have to do it over our entire like 7 million product catalog, because that becomes extremely expensive. So this process that we built out is one that took us a good bit of like R&D trying to fiddle with it to try and get it to actually work well. But I think once we figured it out, it's actually fairly intuitive. So I hope you guys think so as well. So when we start, we have say we are doing a 3-task problem, and we have 3 data sets, so color, pattern, and style. We can basically go ahead and pre-process and prepare these things with whatever way makes the most sense, or whatever makes the most sense for the framework that you're using. So building your data loaders or data generators respectively. Once these are built, you can basically shuffle the batches randomly. So what we're doing here is creating this kind of grab bag of batches that we will then start to randomly sample without replacement. And what happens, so in this case, we draw a square, which is a color batch. So we take the color batch and feed it into the core model. And the core model is actually, we're going to let it output the probabilities and scores for each of the 3 problems. But what we're going to do is only calculate the loss for color, because this is a color batch, and actually only color is marked in this data set. So then what we do is we use that color loss for backpropagation for the specific iteration in this epoch. So in the second iteration or other iteration, say we pick a circle, which is a pattern batch. We take that pattern batch, feed it through the network, and we let it output the probabilities for color, pattern, and style. but we just calculate the pattern loss and use that for backpropagation. So then basically the training epoch ends when we sample the last batch, feed that through, and use that specific batch's loss for backpropagation. So the end result of this is that you get a model or a multitask network that when you feed a sample through, can now actually do very, I guess, reasonable, strong predictions for all of these categories, although it's never actually seen a sample that has been marked with all three of these categories. So for us, this quarter was kind of a fun, successful one because we were able to build out these two processes. And then with it, we're able to physically expand and sort of expand to new categories and continue to perform well on the categories we'd actually built previously. So then in kind of quick wrapping up and I guess, going forward. So quarter one, we really demonstrated that these multitask attribute models are feasible to build in a, I guess, full neural network ensemble type way. Then in quarter two, we sort of showed that we can expand these architectures and we can expand these networks to do new categories, which is sort of a core component of our attribute modeling problem at Shoprunner. Then in quarter three, we're really looking to continue to deploy improved versions of our models. So certain categories that we built, there's some weak classes. So we basically want to go through and augment those sections of those data sets with ways that make sense. We're going to continue to use these methods to build out new categories. So like I said, it never ends. So we will keep on marching along. Then having solved some of the, I guess, backend infrastructure type problems, mostly around Shoprunner not having hosted these gigantic neural network ensembles in our Flask API endpoints before. So now we're at a point where we think we can deploy them and not actually crash our company's servers, which is good. And basically, since these attribute models are now at these sort of very strong points, we want to start using them as feature extractors or as components of other pipelines. So like visual similarity in search, style personalizations for our users, and things like outfitting, which are kind of very R&D things that our company is working on. So that's actually all I have. And questions?
Perfect.
Oh, and as a quick note, this is our team's unofficial team logo. Basically, when I joined up, we were looking to change it from our pygmy goat logo to something else. So I suggested the horse that Andrew Ning drew during his deep learning AI course. But our director shot it down because he really likes pugs and wanted a pug. So I basically photoshopped a pug onto it and he approved it. So, yeah.
Thank you very much for the talk. It's very nice to see Bert in the wild. I want to ask two questions. First one, when you train the model, is quite large model like Bert itself to train. If you train end-to-end Bert with ResNet, what kind of backend did you use for training? And second question, for scaling up, I'm not asking about Flask APIs. It's more like how you justify the cost of running those models on like GPU or TPU instances, and like how much do you like manage the revenue from those models?
Yeah. Okay, cool. So in reference to the first question around sort of the backend and scaling and how we train it, we're actually training on AWS instances. So most of them are being trained on, I think, P3 instances, either the P2 or either 8 or 16. I forget what the larger ones are called. But for now, we're mostly doing single GPU training. I think at a point where the models get larger, we'll probably have to start doing the larger instances with multi-GPUs and some parallelism. But for right now, the models can be fairly comfortably trained in a reasonable amount of time on those single, like, I guess, P3 instances, AWS. And then in reference to sort of how we're scaling it, what we end up doing is we take the models and we kind of do so the first thing we have to do is really like label our huge existing product catalog. So that's kind of a big one-time cost for us. And then after that, we're kind of doing smaller incremental updates. So for us, we're fine running these services on CPUs. So it's not actually as expensive as if we were hosting them on like P3 instances or something. So we basically have that one large computing section where we kind of get the entire product catalog up to date. And then we're just doing daily batches, essentially, to get new things.
So for the like the last bit where you have 3 different categories of data sets, like you're trying to predict color, pattern, and style, then for the final loss, I'm not sure I get why you have to separate, like for each batch you have a you separate out like only one loss at a time instead of just adding them together like what you did before?
Yeah, so I've done both. I've done versions of both, but essentially, if you have the sort of adding the losses together, so you take a like pattern batch, color batch, and style batch, and kind of feed them through, add their losses together, and do backpropagation. You actually have to like reduce the batch sizes down, so it actually becomes quite a bit slower to do the training. So rather than kind of feeding the one batch through, which is much larger, do the single round of backpropagation, it's kind of a speed trade-off that we found in doing the, I guess, training cycle.
Hi, so we're working on similar problems at Stitch Fix, and one thing that we have had trouble with is with outfits. If you have like a jacket over a shirt, how do you get the shirt? Have you come up with tips for that?
Yeah, so that's one that we've also run into, given that we're like in a very similar domain. So that would kind of be, you might have to build very specialized like segmentation models that are basically tailored just to get that type of outfit. So that's kind of my thought on it currently, but we haven't really dove into that very deeply. We have a lot of other initial things to figure out first.
Sorry, and for this scale of this computation, you have 3 data sets. You split into 3 data sets. Roughly, how big are they, each of them, when you do the for the training?
Yeah, so each data set's like 100 to 200,000 products, essentially. So they're not like super huge. We're not using like all of our existing product catalog. We're basically just using sections that we have existing labels for, or something analogous enough to allow us to train quickly. And then we're basically going through, and if there are certain sections of those data sets which are messy or not clean enough for our usage, then we're basically trying to figure out ways to go back and add on additional samples to those sections. But yeah, for now, it's 100 to 200,000 things per data set.
Anybody else?
Yeah, regarding the use of Bert embeddings, did you try more simpler embeddings and compare to Bert in order to get how much the gain is? Because in our case, the training of Bert takes quite a lot of resources. We abandoned it for the time being, waiting for new, more efficient techniques. We use IDF, and it's working more or less well. Have you done the comparison with another simpler methods?
So we haven't done it for attribute modeling, but for basically another set of deep learning that we were doing for like our taxonomy categorizations, we were practicing or trying to do initially with TF-IDF matrices, but we were running into computational issues with the ways that we had built those pipelines. Basically, like the large number of categories and large amount of data, we were kind of running into bottlenecks in training. So then that team kind of switched over to using OMFIT with the like FastAI library and Bert. So we kind of built out these pipelines and the ways to train it when we're doing the taxonomy classification work. So then when we started doing the attribute modeling work, we kind of just piped that over since it was basically analogous from our pipeline side. So we haven't done it explicitly for attribute modeling.
Anybody else? Okay, cool. Let's give him a round of applause, please.